Hello everyone. So in this video, we're going to resume from our previous video where we ran an analog to digital converter with the Artix-7. But this time, we're going to take the output of that analog to digital converter and pass it through a digital filter so we can filter out higher frequencies in real time. So the way we're going to do this is through using MATLAB to generate the filter for us, and then we're going to take that generated code and instantiate it into our design. So we don't really need to understand how to make a filter from scratch. So to get started, you're going to do filter, designer, and then this comes up, click close. FS, that is how quickly the filter samples. Ideally, it would be really high, but you're going to run out of resources. So you have to use a really small clock. So we're going to use 50 kilohertz to be what drives our filter. And this is the pass frequency. Say we want to have it be 6,000 hertz pass through. Then let's say we want to stop and everything after 10,000. We want it to be a low pass. And then we can leave everything else the same. This might happen. Okay. So then from here, we go to this one, this third one. Oh yeah, and this thing that popped up, this is the frequency response of our filter. So it's not too terrible. It attenuates. So it's doing all right. So then we're going to go here. We don't want fractional bits because the output of our analog to digital converter, it did not have fractional bits. It was just an integer. So we want this to be just an integer. Then we click apply. Then that's everything for that. So we go to targets, generate HDL. So in here, there's some things we need to set. We need to so that right there can be left how it is. This can be left how it is. That can be left how it is. But we want to change the radix of the input stimulus, because the input stimulus affects the filter block. Because our analog to digital converter was 12 bits, we're gonna need a lot. So 24 bits total, 8 bits fraction, and these numbers are good because for 24 bits total, it means that when we use the ADC output, it's going to have a lot of leading zeros. So it's not going to like overflow or anything. Because this filter, it can only process signed values, but our analog to digital converter from the previous video had an unsigned output. So to make the signed output of the chip, the ADC chip, function as an input with this signed filter, we need to have the filter have a much bigger input, so then we can pad the ADC output with zeros. So that's why we use 24. And we can leave the fractions 8. Apply. So then we get this. And it's good to leave some decimal, so that EN8 means that there's 8 fractional bits. And that's okay, even though we're not going to use any. Because the filter, it does its math in fractional bits, so it's just better to have some. Anyway, once we do that, here, don't need to do any of these. Oh yeah, it would be nice if this could work, but it cannot work. This code, MATLAB, cannot generate a real test bench. It's up to us to do that, and I'll show you later in the video how that happens. Click apply, and the code generation, like yeah, it's going to generate code in your working directory. So right now we're in MATLAB files. That's the directory we're in. Just let me go to that right here. So when I click generate HDL, it's going to generate. So it's generating right now. Yeah, all that stuff is coming in. Okay. So that has generated. And we can find our modules. So yeah, all these V files, these are all files that we can then use in Vivado. But, so yeah, so go to here. All of these things are here. And the reason why they're there already is because I went to this previously and I added a directory, so the project knows to automatically look in this directory and use all the V files as a module. So that's one approach, or you could just add them manually. But regardless, you just get them into your project. And so that's that. Now, so now let's go over how to make a test bench, because that is not that easy to do. Well, I mean, it's not that hard, but it requires knowing how to think about it. So we have our digital filter that got generated. And we need to feed a sine wave in. And we're going to get a sine wave out. So our test bench is going to create this input sine wave. So the way we're going to have to do that is through making a program in Python to create a memory file of, because remember, this in the actual implementation, the analog to digital converter is driving this. So we have a series of 12-bit numbers coming in. 12-bit numbers coming in that implements an unsigned sine wave. So to do that, we need to have a Python program that takes the frequency of the wave we want to represent in a memory file, the number of bits that each value can be represented as, an amplitude scale on like how big the sine wave should be, and a sample clock for how many data points are there going to be per period. So let's say we have the amplitude scale be 1. It's going to generate like this, where 2 to the n is the maximum range that's determined by the number of bits. So the number of bits sets the range, and then the amplitude scale determines how tall it is. So if the amplitude scale was like 1/2, it would be like this. So that's that. So I'll show you that program. Okay, right now there's no memory files, but the test bench uses the 3 memory files. Call this one 8. We'll call it 9. It's 15. So we need to go to where we have our Python programs. So we need Python, Control V. So we want this first frequency to be 5 kilohertz, 12 bits. Let's do 0.5. And we want this one to be kind of high. We want there to be a lot of data points. That. So it saved it to there. Let's do it again. It saved it to the directory of our project. Now we're going to do the second program I have to make another one. Frequency 8 kilohertz. Number of bits 12. 5. 1 mega. That's good. Let's do one more. So I have 3 separate programs to generate 3 separate memory files that'll be used. That's why I'm running the program 3 different programs. You can see this one be 15K. It's 12. To scale 0.5. Sample clock. 1 mega. So there we go. Now if we go to our MATLAB files, now we have our mem files here. We go into Vivado. Now the memory files are there. So, oh, and then the third one's there. But so we have our test bench. It's going to test the digital filter module only. So we have a lot of signals here, but only a couple of them matter because in our test bench, this is our instance. We have our input signal, which remember in our MATLAB, it's 24 bits long with 8 bits of fraction. That means our input signal is going to be the analog to digital converter bits, those 12 bits with 4 bits padded here and 8 bits padded for the fraction. So that's our input signal. So for the input signal, do radix, real settings. have the different style analog. Oh, we need to go out. So yeah, that input signal is being generated using the memory files that we made. So we had one memory file for the 5 kilohertz signal, that's this one. Then we had one for the 8 kilohertz signal, that's this one. And then we had one for the 15 kilohertz signal, that's this one. So we have our different frequencies. Then our filter result. So remember, our filter had our data out signal, which is 41 bits. This here was 41 bits, but we're only interested in the first 12 integer bits, so we have our filter result. Just grab those first bits of the integer. So filter result. So decimal, radix. I mean, so yeah, it is very clearly working. At the start, it needs time to do its weird calculations because it's processing the whole thing. But after it's stabilized, it starts updating it. So yeah, this one, very clearly, we can see the 5 kilohertz signal is passing through. But then the 8 kilohertz one, it's starting to get cut off. Starting to be cut off. Then the 15 kilohertz one is completely filtered, so it's just a complete flat line. So our digital filter is clearly working. So I already generated the bit stream for this exact program. So now we can view this exact thing filtering in real time with our analog to digital converter from the previous video. That again then. Alright, so we have our filtered result, very nicely detected. Then we have the output of our filtered result, and it's a lot more blocky because if you remember, our filter was made with a 50 kilohertz sampling rate, so it can only update its output at that 50 kilohertz frequency. If we wanted it to be more accurate, we would use a higher sampling rate, but because they have the ADC chip can update its output quicker than what the filter can in this case. But ideally they would be the same. But just for it to fit on this board, like to have the filter fit on this cheap hardware, I needed to use a small one. So small sample rate. So that's why it's all blocky. But anyway, it is still working. So we have 5 kilohertz. Do it again. So now let's say we want to do a higher frequency. So now we're going to go to 8. So we are at 8 kilohertz now. So we're going to run the trigger. And yeah, it's starting to filter it out. So if you look in our MATLAB, the fpass was 6,000. So 6,000 is when it starts to decay. And then at 10,000, it's supposed to be completely gone. So at 8,000, it's not past 10,000 yet, so it's not completely gone. But So yeah, let's jump the frequency. Let's go to 10,000. So we are at 10,000 now. Now let's trigger. So yeah, now it is completely gone. So that. Hold on. Man, my camera's stuck. Oh, interesting. Well, regardless, that's how. Let me see if I can. Okay, so you've now seen how to make a digital filter with Simulink, and hopefully now you're confident in being able to use Simulink to generate a filter of your choice with whatever frequency you need cut off, with however many bits you need for its inputs and outputs. And you take it, you instantiate it in your design, and then generate the bit stream. And knowing how to make a test bench for it, so then you know the thing you generate the bit stream of will work. So hopefully you're confident in that. As usual, the code and files for everything will be included in the video description. And in the next video, we're going to start the process of building a PID controller for a ball balancing system with our FPGA. And we're going to use a digital filter again in that to sample the noise of the time of flight sensor that we discussed previously. But yeah. Alright, that's all for this video.